Welcome everyone. We're still talking about conservation of momentum, conservation of angular momentum. We're just going to apply it to a scenario where we're actually going to be looking at things that are moving kind of traditionally in a very linear, very translational way, and how we can still apply conservation of angular momentum. Okay? Before we actually get into an example problem and how we set it up, I have a situation for us to first kind of analyze. Okay? Let's say here you are standing on the ground and you're looking up and you see a plane flying overhead. Of course, you know the plane is moving and it's flying steady with some velocity v, and you're some distance away, some distance we'll call r. Well, when we started our unit on rotation, I actually had this little diagram of a person holding on to a string with this airplane moving in a circle. Maybe you remember, maybe you don't. It was a long time ago in terms of our videos. Maybe, for example, a callback, if you will. Imagine there was a string going from the plane and this person was holding on. So at this moment, this plane has a velocity of v and a radius of r. And that's important because while this plane is obviously, you would always describe this plane as going in a straight line, moving translationally, based on some things that we learned. Well, if something is moving at some velocity v, some distance away from a location we call a hinge, we could say it has some angular velocity. And that's true. This plane has some angular velocity relative to this location right here. Even though that's a pretty weird way to think about an object moving in a straight line, it is valid, and that's important because certainly our physics has to always be correct regardless of our coordinate system, regardless of whether we're thinking of objects moving linearly or angularly. So this plane at this moment, with this velocity and this radius here, it has some angular velocity that we could then apply for, say, angular acceleration or angular kinetic energy, and yes, angular momentum. So we can treat objects, even though they're moving in a straight line, as having some angular motion. And that becomes important because when we're going to use angular momentum, or when we're going to try and apply momentum for two different types of motion, we can't mix and match. I can't combine translational momentum with angular momentum. That's not possible. I have to pick one coordinate system to use. Now, if maybe you're thinking, well, Thrasher, I mean, this is still kind of weird, or how come we haven't been using this before? Why haven't we always been using rotational motion for things moving in an airplane? Well, there's a pretty quick reason why you can figure out this isn't a helpful way to think of an object as it's moving in a straight line over time. One moment later, this airplane is now over here, right? It's moving in a straight line. So what has happened to its angular velocity? It has changed because a few moments later, the plane, even though it has a constant velocity, it now has a different radius away from us. The radius is changing over time. If we were trying to be weird and actually look at this object from an angular perspective over multiple time periods, you would need calculus because the radius keeps changing. So it's not helpful to look at this plane that's moving in a straight line in a rotational sense over a course of several seconds, but in a moment. For this moment right here, yeah, it has some equivalent angular velocity. At this moment right here, it has an equivalent angular velocity, and therefore it has an equivalent angular momentum, an equivalent angular, say, kinetic energy, okay? That's really why it's going to be helpful. So, okay, so let's see this play out. I have right here another diagram. This is kind of a callback to when we were looking at doors and we were kind of having this overhead perspective. So I have this door here, I have a hinge, and let's say, man, I am firing a bullet into the door. So I've taken a gun, bam, I fired a bullet, the bullet is flying, it's gonna hit and slam into the door. Let's assume the door is at rest, we'll say, okay, and then the two things embed, and the door, even though it's starting at rest, after it slams in or gets hit by the bullet, it's going to start rotating like this with some final angular velocity, okay? Now, you don't have to memorize it, but the angular inertia, or the rotational inertia for a door is going to be one third, the mass of the door, the length of the door squared, where the length of the door is just that. It's the overall length here. That's L, okay? And remember, for a particle, when we were first learning about rotational inertia, we derived this equation, where m is the mass of the particle, the mass of the bullet in this case, and r is how far away it is from the hinge. Now this bullet is moving translationally, but right here, right at this moment, right before impact, or right when it impacts, well, just like that airplane, I can think of this bullet as angularly having some motion, having some momentum. And it has a rotational inertia at this moment based on I, and we're going to measure both of these things from this hinge here. Okay, it has an angular velocity as well. Oh, this is what I mean by at a given moment, we can look at even an object moving in a straight line as having angular motion kind of qualities. So what would the angular momentum of the bullet be equal to? Remember, angular momentum in general is equal to I times omega, the rotational inertia times the angular velocity. Remember, angular velocity is equal to v divided by r. Well, for this bullet, the angular momentum, again, it's weird because this bullet is moving in a straight line, but at this moment, it has an equivalent angular momentum equal to m, the mass of the bullet, times its radius squared, the radius from some location, some hinge, we'll call it right here, multiplied by, v divided by r, because that's what this omega is equal to. I can simplify that. L of the bullet is equal to, what's r squared divided by r? That's just single r. And I'm going to actually just rearrange terms. That's m times v times r. See that? One of the r's cancel, still have a mass, still have a velocity. What does that look like to you? The angular momentum of a bullet, and in fact, the angular momentum of any particle moving in a straight line is the linear or the translational momentum times r. This is our cousin. Remember, regular old momentum is mass times velocity. For something that's moving in a straight line, it's almost like a conversion. The conversion for an object moving in a straight line, well, it's based on that linear momentum multiplied by r. These are now how we can convert from angular momentum, from linear momentum, translational momentum, into angular momentum. And this is important. These two equations, to be honest, I wish they were on the AP Physics equation sheet. They're not. They should be, in my opinion. Okay, but the AP College Board will have questions where you need to know how do you get to, or what's the equivalent version of a bullet moving linearly? It has an equivalent you can convert to a angular momentum, again, at some moment right at, maybe right before an impact. And these are two equations, very important equations you should write down. It's not too tough to derive it, but it's not also super intuitive. So let's see it as it applies to a problem. In my last video, I was kind of deriving this angular momentum for an object moving in a straight line. But we can see, like the example, though I didn't really go over it, if I had a ball that was slamming into a door, or a bullet embedding into a door, at first I have something that's just translating, and then it slams into the door, and then the door is rotating. I have translational momentum and angular momentum. And we can, of course, analyze those scenarios, but like I said before, we can't use and we can't mix apples and oranges, okay? I can't combine in a single equation the angular momentum of the door and the translational momentum of that ball. I can't do something like this. I can't say total momentum is equal to the angular momentum plus the translational. I can't do it. I have to either use angular momentum quantities or only use translational, and we're going to go with this. And we saw that even for things moving in a straight line, I could write it as angular momentum, okay? So, using these equations right here, using these conversions, we can set up conservation of momentum for a scenario like this and just use angular momentum equations. Of course, for an object that's just rotating, we're using the same L is equal to I times omega. And for an object moving in a straight line, we'll use the conversion where the angular momentum is that linear momentum, that regular old translational momentum, times r. And at least that's a little familiar because, torque is force times r. Inertia is regular old mass with an r component as well. So that r that's being kind of tacked on isn't super new, okay? So let's work through now a more detailed example. There's still not going to be a full set of numbers, but let's look at how the algebra would work out. I'm going back to the scenario where I have a bullet that's moving. It's going to slam into a door. It's going to embed in the door. And then the two things are going to be rotating together. How could I set up, because maybe, I don't know, I want to find the final velocity of this door bullet as the two creak and start rotating, the final angular velocity. Well, my system is both the door and the bullet. So obviously there's forces and there's torques as these two things are colliding, but those are internal. For my system, there's nothing outside interfering, so the initial total angular momentum needs to equal the final total angular momentum, right? Now, in the beginning, let's say the door starts at rest. Does the bullet have some angular momentum? Yeah, it's weird, but remember, there was a conversion. So yeah, we can say that that bullet has some angular momentum, plus the angular momentum of the door. It's not moving, so it'll probably be at rest. These are the initial quantities. And if they stick together, what did we do? We treated them like one big object, the bullet plus the door. Okay, well, what was my conversion? For an object moving in a straight line, the angular momentum is just the translational momentum, m times v, that's easy, times r. And again, we're applying this right before the bullet hits the door, right as that impact is taking place, this r value right here. Plus, now again, for an object that's rotating, you might have to be given it. For a door, for a rod rotating about the end, it's the rotational inertia of that door times its initial angular velocity. And here I'm going to be adding the two, the initial or the rotational inertia of the bullet plus the rotational inertia of the door times that final velocity, okay, omega prime. So this right here, I'm just going to put in m times v times r plus 1/3, 1/3, because I'm giving it to you, the mass of the door times L, the length of the door squared, times omega naught. Oh, well, it's starting at rest. This whole thing is going to cancel out to 0 anyway. Plus, for again, a point particle, for a point particle, I of a particle is equal to simply mr squared. That's the one that you should just know. Okay, so that's mr squared plus 1/3 ml squared times omega prime. Okay, again, if we're saying the door starting at rest, this whole thing is just going to go to 0. So that whole thing cancels out. So what am I going to be left with? The mass of the bullet times the velocity of the bullet times the radius, where it's impacting measured from that hinge, this distance r, that's equal to the mass of the bullet times r squared plus 1/3 ml squared. Because now all this thing, this whole setup, the door with the bullet embedded in it, that's going to be rotating, okay, at some velocity omega prime. If you wanted to solve for omega prime, I know I don't give you enough numbers to get an actual answer, but omega prime is going to be equal to mvr divided by this whole thing in parentheses right here. Okay, that's going to be mr squared plus 1/3 ml squared, right, like that. Now, again, what's the most important thing? I can still say the initial momentum is equal to the final momentum. I can even include things that are moving translationally and look at the momentum and combine it with something that's just going to be rotating. I just have to always use the same type of momentum. I can't mix translational and angular momentums together. So I convert the translational momentum into a form of angular momentum. I add that with the angular momentum of the door, and I can still solve for it, okay? So you can still look at scenarios where things are colliding and sticking, even when one of them is translating and one of them is rotating, okay? You just have to always use the same type of momentum. You can't mix and match. Of course, you'll be getting practice with these. There are both conceptual questions and, as you can guess right here, some math questions that can be associated with this type of scenario. But it does show up on the AP Physics 1 exam, so getting practice with these types of scenarios is important. All right, that's all. I'm signing off. Thanks for watching.